Hello viewers, welcome to video number 119 of the channel MALACHEMPHILIC. And this video number 119 is the 59th episode of Chemical Thermodynamics, where the topic is thermodynamic functions of mixing. And today we'll discuss Gibbs free energy of mixing. So let's start. See, when two or more substances are mixed, then there occurs a change in the measurable properties of various components of the system. Okay, and then what is thermodynamic property of mixing? Means before mixing of different components, if you add a particular property of all the components, that is the sum of the initial property of all the components before mixing. And after mixing, what will be that property if you measure? That will be the final property. So thermodynamic property of mixing will be final property minus sum of this initial property of all the components. Okay. Now, free energy of mixing of ideal gases. Just we'll consider, see, we are considering, 1 minute, I'll make it this. Here we are considering a vessel or container, okay, where there are two partitions, and because of these two partitions, this container is divided into 3 compartments. Each compartment we are taking a pure gas, okay, pure gas, not mixed. This is one pure gas, this is one pure gas, and this is in this compartment another pure gas. Okay. Here compartment 1, the number of moles of this gas is N1, here it is N2, compartment 2, here it is N3. And these partitions are removable. That means if you remove the partitions, then what will happen? The gases will mix up. The situation will be like this. It will be mix up. All gases will be mix up. Okay. Then when they are mixing up, then a particular property, thermodynamic properties, say Gibbs free energy, entropy, enthalpy, everything, there is a change. Okay. And what is that change? In this mixed condition or in this mixture, what is that value of this property? Minus this value of this property of each gas in the pure state, minus sum of this value of these properties of each gas in the pure state at same temperature and pressure. That means pressure in these 3 compartments also, this is P, and temperature also remains constant T, at the same temperature and pressure. So now we have to calculate this free energy of mix. Okay, so this curve will come later. Now we'll start. See, delta G mixing, that will be is equal to, we know, free energy in the final state minus free energy in the initial state. Right? Now, free energy of this initial state, that will be the free energy of the ideal gas number 1, then ideal gas number 2, then ideal gas number 3. Okay, and that will be is equal to N1 mu 1 star plus N2 mu 2 star plus N3 mu 3 star. Okay, already in my earlier videos, I told you that G, Gibbs free energy of the pure gas or pure substance is equal to mu for 1 mole. That means when you are taking 1 mole of the pure substance, pure ideal gas, then free energy is equal to this chemical potential. Okay, so this mu1 is the chemical potential of the pure gas 1. Mu2 is the mu1 star, sorry, mu2 star is the chemical potential of this pure second gas, number 2 gas, like that it is number 3 gas. Okay. So this is for 1 mole. Here number of moles are N1 into N3. So N1 mu1 star plus N2 mu2 star, like that. Okay. So this is the pure state. We are denoting it that this star. Okay. Fine. This is for G initial. Now what will be G final? G final will be from Gibbs-Duhem equation. We have seen that if a number of components are there, then G will be equal to N1 mu1. Here this mu1 is the chemical potential of the ith component in the mixture. Okay, now it is mixed up. Plus N2 mu2 plus N3 mu3. Okay. So then what will be delta G mixing? Just now I told you final minus initial. So G final minus G initial. That is the delta G mixing. Okay. Now we'll write down. So G final will be which one? G final is equal to N1 mu1 plus N2 mu2 plus N3 mu3. This is final minus what is initial? Initial is N1 mu1 star plus N2 mu2 star plus N3 mu3 star. Okay, this mu1 star is the chemical potential of 1 mole of ideal gas 1 in the pure state. Okay, at that temperature, pressure T and P. Okay, right. Now, here one thing we have to understand. Already I explained. See, we know that in the mixture, we know that mu I is equal to mixture of ideal gases we are taking. That is mu I0. That is the standard chemical potential of the ith component plus this is RT ln Pi. Pi is the partial pressure of this gas. Right? Fine. Again we know that this partial pressure, that will be the mole fraction of that component into this total pressure, which is here P. So what we can write? I can write it as mu I is equal to, mu I is the chemical potential of ith component in the mixture. Once again I am telling you. So this is mu I0 plus RT ln, what I can write? Xi into P. So this one I can write it as mu I0 plus RT ln P plus RT ln Xi. Okay, log A into B means log A plus log B. Now this one, that is your, here again, mu I is equal to, this is your mu I star, that is the chemical potential of the pure ith component or pure component, any pure component at that temperature and pressure. Here it is P and T. Okay. Then plus RT ln xi. Okay. From here, what can I write? We can write it as, what can I write? We can write that mu I minus mu I star is equal to RT ln xi. Okay, this one we can write it. Fine. So now we got delta G mixing is equal to N1 mu1 plus N2 mu2 plus N3 mu3 minus N1 mu1 star, like that. Once again, next page we write it. So this delta G mixing, that is equal to N1 mu1 plus N2 mu2 plus N3 mu3, then minus N1 mu1 star plus N2 mu2 star plus N3 mu3 star. We got it. So from here we can write it as delta G mixing, that is equal to, if I take N1, then mu1 minus mu1 star, okay, plus, if I take N2 common, because N1 mu1 star, N2 mu2 star, then it is mu2 minus mu2 star plus N3, then mu3 minus mu3 star, right? And just now we have seen that this mu1 mu I minus mu I star is RT ln xi. So in this place, what I can write? Delta G mixing, I can write it as N1 RT ln x1, right, plus N2 RT ln x2 plus N3 RT ln x3. Now both the sides of the equation will divide it by total number of moles, right? So we write like this: delta G mixing divided by N is equal to N1 by N RT ln x1 plus N2 by N RT ln x2 plus N3 by N RT ln x3. Can write. Now number of moles, where N is my total number of moles. Okay, so here I write N is nothing but total number of moles. That is equal to N1 plus N2 plus N3. Okay. So, what can I write? We know that number of moles divided by total number of moles, that is the mole fraction. So, what can we write? Delta G mixing divided by N is equal to RT x1 ln x1. x1 is the mole fraction of the gas 1 in the mixture, right? Then plus RT, we should have taken common here, RT x2 ln x2 plus RT x3 ln x3, right? So this one is equal to, if I take RT common, that means x1 ln x1 plus x2 ln x2 plus x3 ln x3, right? So from here, delta G mixing, I can write it as delta G mixing. I can write it as, this N will come here, N R T summation of, say if more number of components are there, xi ln xi. Okay, this is the expression for delta G mixing or free energy mixing of the ideal gas. That means change of free energy due to mixing, right? Now let us consider a mixture of, let us consider an ideal gas mixture of two components. Okay. So delta G mixing, what it will be? N R T, then x1 ln x1 plus x2 ln x2, right? x1 is the mole fraction of component 1 in the mixture. x2 is the mole fraction of component 2 in the mixture. We know that x1 plus x2, that will be is equal to 1. Therefore, what we can write? x2 is equal to 1 minus x1. We can take this one. x2 is equal to 1 minus x1. Right? So, then we can write delta G mixing, that is equal to nRT, then x1 ln x1, right, plus 1 minus x1 ln 1 minus x1. You can write it. Okay. Now, delta G mixing will be maximum or minimum if the first derivative means we have to differentiate here with this is variable with respect to x1. Okay, if the first derivative is 0, right? So delta G mixing will be maximum or minimum if the first derivative is 0. Okay. That means what is that first derivative in the sense? This is the variables, no? x1. So we have to differentiate with respect to x1 at constant temperature and pressure. So dole of delta G mixing by dole x1 at constant temperature and pressure, that will be is equal to, now I have to differentiate this part, right? So this is nRT, this is independent of this x1. So now inside you will differentiate. Look at here, there are two functions. So how to differentiate? First function differentiation of the second. ddx of ln x or log x is 1 by x. So into 1 by x, x1 here, plus second function is ln x1, differentiation of the first, ddx of x is equal to 1. So here d by dx1 x is equal to x1 is equal to 1. So into 1. This part is over. Plus. Okay. Now we have to differentiate this part. Right? Once again, plus first function is 1 minus x1. Okay. Then differentiation of the second. Differentiation of the second means 1 minus x1 is there, no? So first we have to take the differentiation of this one. So ddx of 1 will be 0, ddx1 of x1 will be 1, minus 1. So it is minus 1 and then into this, now ln, that means 1 by 1 minus x1. Okay. So first function differentiation of the second plus second function. What is second function? That is ln 1 minus x1 second function. Differentiation of the first will be ddx of 1 is equal to 0, ddx of x is equal to 1. So it is minus 1. So this is the differentiation. Okay. Now we look at here what is left over. See, x1 getting cancelled. Then here also 1 minus x1 is getting cancelled. So what is left over? Left over is nR. And this is equal to 0. First derivative should be 0. Okay. So nRT, then this is 1 plus ln x1. Okay. Then this is getting cancelled. So minus 1. Okay. Then minus ln 1 minus x1. 1 and this is equal to 0, and this is your dole of delta G mixing by dole x1 at constant temperature and pressure. Right? Now from here you see this 1 and 1 is getting cancelled. So left over is ln x1 minus ln 1 minus x1 is equal to 0. So we'll go to the next page. So what we got, that is dole of delta G mixing by dole x1 at constant temperature and pressure, that is equal to nRT, and what we got, ln x1 minus ln 1 minus x1. So ln x1 minus ln 1 minus x1, this we got, and that is equal to 0. Now, so this is 0 means either this term is 0 or this term is 0, but nRT, this cannot be equal to 0. So therefore, what we can write, ln x1 minus ln 1 minus x1, that is equal to 0. So here what can we write? Log A minus log B. So ln x1 by 1 minus x1 is equal to 0. Log x is equal to 0. That means this one will be 1. So therefore log, because we know log 1 is equal to 0. So therefore x1 divided by 1 minus x1 is equal to 0. Is equal to 1, because log 1 is equal to 0. Okay. So here it is, x1 is equal to 1 minus x1. So here 2x1 is equal to 1. So x1 is equal to 1 by 2, half. Okay. Again, x1 plus x2, that is equal to 1. Therefore, x2 will be equal to 1 minus x1 is equal to 1 minus half is equal to half. So this delta G mixing is minimum or maximum when x1 and x2 values are half and half. That means when x1 is to x2 is 1 is to 1. So therefore delta G mixing is minimum or maximum at x1 is equal to half, x2 is equal to half, that is x1 is to x2 is equal to 1 is to 1. Okay. Now next part is whether this delta G mixing will be maximum or minimum. right? So for that, what you have to do? We have to take the second derivative. Second derivative, that means dou square of delta G mixing by dou x1 square at constant temperature and pressure. So what was the first derivative? First derivative was, that is, after derivative what we got? ln x1 by 1 minus x1. So ln x1, that is first derivative, actually this one, nRT ln this one, nRT ln x1 minus ln 1 minus x1. So is equal to nRT. Now we have to differentiate, that is ddx1 of ln x1 minus ln 1 minus x1. ln x1 minus ln 1 minus x1. This one. Okay. So now separately we'll do this differentiation. Okay. ddx1 of this thing separately we'll do it. I'll do it here. So here I'll do it. That is dd dou x1 of what? ln x1. So I can write it as ln x1 minus dou x1 of ln 1 minus x1. Okay, I'll do this one. Then what will be this value? This will be is equal to 1 by x1. Okay, and this will be is equal to, this will be minus, this will be is equal to, first of all we have to differentiate this one, that means minus 1 into 1 by 1 minus x1. Okay, so this is equal to 1 by x1 plus 1 by 1 minus x1. This we got it. Okay, right? So anyhow this is the constant term. So next page I'm writing this term only. So 1 by x1 plus 1 by 1 minus x1. So here 1 by x1, then plus or minus plus 1 by 1 minus x1. Okay, so what will be this one? If you take the LCM will be x1 1 minus x1. Okay, so it will be 1 minus x1 plus x1. So it will be is equal to 1 by x1 into 1 minus x1. Okay, so this term 1 by x1, say x1 is 0.5. 0.5 into 1 minus 0.5. Okay, so this term, that is x1 into 1 minus x1. What it will be? x1 minus x1 square. Okay. This I can write it as, say, x1 minus x1 square. This term will be positive. Okay. So, this will be positive. So, this 1 by x1 minus x1 square, this will be positive. Okay. This will be positive means, what was these things? This second derivative, nRT, that is positive, into that one. So, both are positive. Okay. So, what we can write? That dou square. So, therefore, dou square, that is delta G mixing by dou x1 square at, that is the second derivative, constant temperature and pressure, which is equal to nRT into 1 by, either you write x1, 1 minus x1, or you can write this one, x1 minus x1 square. This will be positive. Positive means, that is that delta G mixing, therefore delta G mixing is minimum. It is not maximum because it is coming positive. Minimum at x1 is to x2 is equal to 1 is to 1. That was half and half. Okay. So, this is our free energy of mixing. Okay. That expression we have found it out. And one more thing, that it is minimum at 1 is to 1. So, that's why now we'll come to that graph. So, if we plot this delta G mixing versus this is your x1, okay, then you will get the minimum at x1 is equal to half. Here is the minimum, that means x1 is equal to half. x1 is equal to half means x2 also is equal to half. So, this is the graph. So, for the mixing of ideal gases, when you are mixing the ideal gases, this free energy decreases, or the change in the free energy is negative. It decreases. Okay. Achha, that you can explain from this equation also. I'll show you. Okay. Look at here. In this equation, see, overall equation is xi ln xi, right? Xi is less than 1 because total mole fraction is 1. Xi is less than 1. For any component, mole fraction is less than 1. So, ln xi, log xi will be negative. That means delta G mixing decreases. During mixing, free energy changes decrease. That means free energy decreases. And this is the expression. So, hope you have understood. Thank you.